in India in 2020, and is currently affiliated with the Artificial Intelligence and Biomedical Imaging Lab and the Center for Biomedical Image Computing Analytics at the University of Pennsylvania. His major fields of interest include biomedical image analysis, cancer imaging, radiogenomics, and computational pathology. And he has developed various algorithms for segmentation of brain tumors based on deep learning, as well as research on extracting radiomic features for the overall survival prediction of patients with glioblastoma. And today we're excited for him to talk to us about the Brain Tumor Segmentation Challenge 2023. Welcome, and you have the floor.
Thank you for the kind introduction and inviting me. So most of the initial slides are talking about like data privacy and these things which are already covered by Amber in previous talk. So I would be giving briefs about that challenge, what the data is, what are the specific tasks, and what is the timeline, and how to participate, and how you can easily generate the baseline results for the challenge using a Gandalf tool, which is indigenously developed at our lab. At any point of time, if you have any specific question on specific slide, otherwise we can discuss at the end. Nowadays, like these two terms, like machine learning, deep learning, these terms have revolutionized whole segmentation, classification, and detection task in our medical imaging domain. And this has been possible because of these three things: data, computation, and algorithms. Like we have ample amount of data, we have computational resources like graphic processing units and all, and we have really complex algorithms which are addressing all these three tasks. Most of the research revolves around natural images, but when we translate these methodologies to medical data, there are several hurdles. Like when we deal with the medical data, we have patient privacy, HIPAA compliance, GDPR, then we need IRB approvals, we need to anonymize, there are various acquisition protocols and all. Again, this is similar to what Amber already explained, like all these data sets are already available with the specific hospitals, and because of these regulatory issues, don't have access to data of all these hospitals. So the easy way to have access to these medical data sets is look at the challenges which are hosted at Medical Image Computing and Computer Assisted Intervention Conference and IEEE Symposium in Biomedical Imaging meetings. So if you look at these conferences, there are several challenges hosted every year where anonymized data sets are provided, and challenge organizers deals with all the pains of IRB and compliances, and challenge organizers identify neuroradiologists or other experts in the field of, and then let's say I'm developing some methodology in University of Pennsylvania, and someone from Europe is also developing some algorithm, let's say for brain tumor segmentation. And in the paper, they report like, we have achieved 90% accuracy. But how to confirm if the number mentioned in the manuscript is valid or true, or it's just an exaggerated number? So this challenge, most of the challenges comes with online evaluation portals where you can submit your results, predictions, and you'll get the numbers. Again, the challenge design documents are already available on Zenodo. So challenge organizers cannot change the rules of challenge to give undue advantage to selected population or participants. These challenges come with timely publications. Like usually challenge participants are invited to submit their methodology to post-challenge manuscript, and as earlier speakers mentioned, these manuscripts attract a great number of citations. So we are contributing for Brad's challenge. So in Brad's challenge, the The data provided comes from 4 multimodal MR scans, T1 post contrast, T2 weighted, and T2 flare. And these MRI data have GBM tumors and subregions. So let me quickly explain what Brad's data set have. So if you look at the figure D, we have provided multimodal MR data along with 3 labels: edema, enhancing tumor, and necrosis. I will be discussing these next slides. And, and the evaluation is performed on 3 labels: enhancing tumor, tumor core, and whole tumor. So tumor core, union of enhancing tumor and the necrosis, and whole tumor is the union of enhancing tumor, necrosis, and edematous infiltrating tissues. So So what are the label definitions? So 3 labels are considered for segmentation: ET, NCR, ED. Now ET is the yellow part which we saw in the previous slide. So it is a subregion which is described by area with both visually avid as well as faint enhancement on T1 post contrast. So if we compare a T1 native and T1 post contrast, the enhancing ring is known as ET. It's enhancing tumor. Necrosis is the appearance of NCR region, which is hypointense in T1 post contrast. Here, if you see my cursor, T1 post contrast. And the green, which is edema, and I would like to read these 2 points as it is, because I'm a computational engineer, and this is defined by a neuroradiologist. So enhancing region is defined by abnormal hyperintense signal envelope on T2 flare volumes, which include the infiltrative non-enhancing tumor as well as vasogenic edema in the peritumoral region. Importantly, this is the distinguished from cystic regions and the ventricles. So there is a lot of confusion in the edematous infiltrating tissues, and we sat with the neuroradiologist and defined these terms. So at challenge, we would be looking at enhancing tumor, necrosis, edema. So historically, the Brad's challenge is organized from 2012, and when the Brad's challenge was started, it was mere with only 50 cases. And in the subsequent challenges, more data sets were added in preoperative scans, and more manual annotations were provided. And from 2017 onwards, much more data set from TCI was included. And in the most significant contribution in that's 2021, we had 2040 subjects, in which 1,251 subjects were from the training cohort, 570 in the testing cohort, and 290 in the validation cohort. So this was a big jump from all the previous Brad challenges. So if you look here, from Brad's 2017 to 2020, there was additional task apart from segmentation is the survival prediction. So the data was provided in terms of number of days, where participants were asked to develop some radiomic feature-based algorithm to predict the overall survival of the patient. And in Brad's 2021, the task, apart from segmentation, the task was to predict the MGMT methylation status of the patient. For Brad's 2021 challenge, we had data from a bunch of institutions from US, from Europe, and one site from Asia. Then we reached out to ASNR society, because practically it was impossible to annotate these bunch of data. And so 60 plus expert neuroradiologists volunteers, predominantly from ASNR society, that spent their invaluable time to generate ground truth labels. As you notice, in 2021, all expert annotators approved to be listed by their names and affiliations, thereby reflecting our transparency and their certainty for the quality of the provided ground truth. And as earlier speaker mentioned, that this needs to be clear at the commencement of the challenge itself, like who would get what contribution in the manuscript. So it's a publicly available dataset and a community benchmark. And so multi-level segmentations for glioma subregions were provided in the BRATS 2021 challenge. Consistent annotation protocol was provided, and a manual annotation protocol. We sat with the neuroradiologist. We created some tutorials like how we annotated using ITK snap or 3D slicer or CapTK, and then appropriate algorithmic evaluation was done, and we involved biostatisticians to have a p-value analysis, like how the methods are statistically significant with the other methodologies. Then a harmonized pre-processing tool was publicly provided. We provided some monetary award, and this challenge was hosted on a Synapse platform. Let me So the challenge design document was publicly available on Zenodo. We provided BRAT's pre-processing pipeline through the indigenously developed tool, which is CapTK, as well as we have provided a federated tumor segmentation platform, and we provided this BRAT's pre-processing pipeline in FATES tool as well. So if you look at the participation in previous BRATS instance, we had more than 2,100 registered teams, and out of these 1,300 plus teams have made more than 20,000 submissions during the validation phase. And we asked participants to submit their containers, like Docker containers, and we reran all these Docker containers on the testing cohort for fair evaluation. So historically, I wanted to talk about BRAT's 2021 challenge, but for this year onwards, we have moved away from glioma, and now we have a cluster of challenges. And this year's efforts are sponsored by MICAI, NCI, UPenn, Sage Bio Networks for the challenge hosting. Lacuna Fund is explicitly for the researchers from Sub-Saharan African, Commons, Neosoma. So these are the entities which are supporting this year's BRATS challenge. So BRATS 2023 is a cluster of challenge. I would like to spend some time on this slide. So we have segmentation of brain glioma, which is a typical BRATS challenge, and we call it as continuous evaluation challenge. We have provided same data set of BRATS 2021, and participants are asked to segment glioma subregions. And we would be stopping at some cutoff time, and we would be giving results in the MICAI conference. Then we have segmentation of glioma in Sub-Saharan African region. So what we observed, like there are a bunch of methods. When we look at the top 10 performing teams, we took out their Docker containers on the data from Sub-Saharan African continent, and what we observed is the issue with the generalizability of the algorithms. So methodologies and the methodologies which were top performed in BRATS 21 challenge could not perform well in the underrepresented population dataset. So we collaborated with the collaborators with Sub-Saharan African continent. We wrote a grant, we got funding, and now collaborators from Sub-Saharan African continent collected data from their region, and we have dedicated challenge on the data from SSA. Next challenge is the segmentation of intracranial meningioma. Here, more than 1,000 cases are provided for the training cohort. And the task is similar to the segmentation of brain glioma with similar intratumor parts. And we already have released a training data of 1,000 plus cases. Next is segmentation of brain metastasis. This is again a challenging task where brain metastases are of like 5 millimeter, 3 millimeter, 8 millimeter, and it's really difficult to segment brain mets. And currently, like neuroradiologists are like working around the clock to prepare this data set, and hopefully by the end of this week, the first batch of training data set for brain mets challenge would be out. Next is segmentation of pediatric brain tumors. We observed that some research groups tried to develop some segmentation model using brain glioma data, and they want to do some transfer learning thing for pediatric brain tumors. So we collaborated with CHOP, which is Children's Hospital of Philadelphia, and other entities from Washington University, St. Louis, and they had the dedicated efforts with CBTN, Connect, DIPGR, and and we have 100 plus cases ready to go for Brad's pediatric challenge, and the data is already publicly available. Then when we were collecting data set from challenge 1 to challenge 5, we observed that there are different clinical acquisition protocols, and not all these four modalities are always acquired. And sometimes like T2 is not needed. Some people say T1 weighted is not needed. Sometimes your contrast is not needed. So there are missing modalities. And sometimes during acquisition, because of some issues and all, some brain tissues are missed. So and nowadays these generative adversarial networks are pretty popular in generating missing information. So we explicitly created some data sets where only three modalities are provided: T1, T1 post contrast, and T2. And we asked participants to generate T2 flare. Or let's say T1 post contrast is missing and you need to generate T1 post contrast modality out using rest of the three modalities. So these are the dedicated challenges for synthesizing the MR data. And nowadays, these because medical data is less, people go for heavy augmentation methods. Like only 100 patients data is provided for, let's say, pediatric brain tumors. So what people do, people go for various augmentation techniques, like they rotate the data, they distort the MR images. So we want to evaluate like which of these augmentation techniques are best suited for a deep learning methodologies. So we have provided uh, a baseline algorithm for brain tumor segmentation task, and you are expected to have your own augmentation techniques. And we will be evaluating like which of these augmentation techniques are the more robust and performs well for tumor segmentation task. Apart from this, this is a feasibility assessment of segmentation across all tumors. I would say this is similar to medical image decathlon, where participants are asked to use data from challenge 1 to challenge 5 and develop most robust segmentation algorithm to segment necrosis, enhancing tumor, and edematous infiltrating tissues. This is the timeline for this year's BRADS challenge. The dataset is already released, and we would be having validation phase sometime mid of this month. And participants are encouraged to submit their Dockers in form of ML cubes by the end of July, and we would be running Docker containers on the testing cohort. So feel free to register here on the Synapse platform. And top performing teams would be invited for oral presentation at MICAI, and we are planning to invite all the participants for poster presentation at MICAI in Vancouver. Again, we need to identify what is the most robust mechanism to have ranks for the methodologies from the participants. So in BRADS, we have enhancing tumor, tumor core, and whole tumor, and we calculate DICE similarity score and Hausdorff similarity score for all these three components. So let's say for one patient, we will have 6 matrices, 3 regions and 2 matrices. So each team is ranked for 3 regions and 2 evaluation matrices. Let's say we have 219 subjects in the validation phase. We will have 1314 ranking. And in, let's say, testing phase, we will have 3420 rankings. So the team which performs best in all the rankings would be the winner. So the final ranking is based on average of all these rankings. These are normalized by number of teams, and we have called these as BRAD segmentation score. So the team with the best BRAD segmentation score will be the winner. You know, some top performing teams did not differ much in terms of computational scores. So we did pairwise comparison and find out the statistical significant difference with 100,000 permutations to identify like which teams are statistically significant or insignificant. Again, this is all about the Pratt challenge and all, but there are several issues with the reproducibility of the results. So we developed a tool indigenously at our lab, which is known as Gandalf, generally newest deep learning network, which will give a baseline performance without writing a single line of code. So the motivation to go for this, like when you go for any deep learning framework library like TensorFlow, Keras, nowadays PyTorch is pretty popular. It should be easy to use and generate baseline results quickly. It should support multiple architectures. It should handle various imaging modalities. Like we have seen, like ImageNet, these things were primarily developed on like natural images. But when we talk about CT, MR, X-ray, so the framework should handle various imaging modalities that should support robust data augmentation, that should tackle segmentation, regression, classification. It should be easy to deploy in clinical workflows. We have seen like tons of papers are coming in NICAI and ISB conferences. But when we actually go to the clinics, it's very difficult to deploy a single segmentation algorithm in actual clinical workflow that is on PATs or these things. Again, the framework should be open source. It should be a playground to novel computational methods, and it should have continuity of work in academia. Let's say a PhD student is developing something in 4 years, but once he left, that work should be continued for the further research. And this leads to the development of Gandalf, which is generally newest deep learning framework. The paper is recently published in Nature Communication Engineering, and this is with the lower barrier to deep learning framework. And this is written in PyTorch, and this supports multiple tasks, as I explained earlier, like segmentation, classification, regression, and multiple input image in parallel, multiple labels. Cross validation is provided, robust data augmentation techniques, and multi GPU training is provided. This works for radiology as well as pathology data. And let me quickly show you this. Yeah. So in Gandalf, we have provided various IOs and anonymization. So if you are dealing with the DICOM data, we have provided pipelines which will convert from DICOM to Nifty. All PHI is removed. Sometimes histology images are coming with a small image where PHI is provided. Again, this can be removed by IO anonymization. We have provided dedicated scripts to the data, like intensity normalization, resolution normalization. Again, various augmentation techniques like rotation, blur, scaling for radiology, and color jitter are provided for histology images. Then various network topologies like BGG, ResNet, DesNet, UNet, whatnot, like more than 25 plus model architectures are provided. In conventional machine learning, cross-fold validation is pretty popular, which is not popular in deep learning based methodologies. We have provided utility to have cross-fold validation and various post-processing methodologies to remove false positives like connected component analysis. Some morphological operations are provided for as a post-processing techniques. So these are the current features. Like it's very easy to use. It's simple YAML based configuration and a CSV file, a YAML where you need to provide all the configurations of your training strategy, and a CSV file uh, which will which will be pointing towards your data. In the interest of time, I will not be going into the details of Gandalf, but the tool is completely open source. You can use and modify as per your need and application. This is very driven effort and led by Sarthak Pati, who is lead software developer of our lab. And these efforts are backed by ML Commons. ML Commons is a community where all collaborators from industry, academia come together and develop open source tools. So from University of Zurich and Dana-Farber, Intel, Google, and a bunch of institutions. these are the key takeaways from Gandalf. It's easy to use for experienced as well as novice users. We have provided tutorials at the repo of Gandalf, and we also host the open community calls weekly where you can just chime in and discuss whatever issues you have with the Gandalf, and we are ready to help with it. So the aim of Gandalf was to provide a playground where participants can use data from various challenges, and you have a dedicated tool that you can use to generate the baseline results of these challenges for easy entry into these challenges. And we have provided dedicated tutorial where let's say if you are working on Brad segmentation task. So we have provided YAML file, sample CSV file, and how you can use these YAML and sample CSV to generate baseline results and can be part of Brad's challenge. Thank you so much.